right, welcome everybody, thanks for coming. So this is the last lecture of this series that Professor Nesvorný is giving as an invited professor here at Collège de France. So as I announced yesterday, today he will build on what he presented last week and present the expected orbital distribution and size distribution on near-Earth objects and compare with observations, and so address also the issue of collisions with the Earths and the impact risks on our planet. So, David, please.
Okay, so we will talk about the NEO population, and we will talk about the population-wide statistical properties of NEOs, including issues related to planetary defense, how many bodies are expected to impact on the Earth, and scientific issues. What are the orbital properties of NEOs? What are their physical properties and stuff like that? But before we do that, I would like to highlight two individual NEOs. This is Ryugu and Bennu. These two objects were targets of sample return mission by Hayabusa 2, Japanese Hayabusa 2, and the NASA OSIRIS-REx. Now, both these missions were successful. They returned a significant amount of material to the Earth to be studied in labs. And one of the most interesting results that comes from these studies so far is that the isotopic composition of these two objects is similar to CI chondrites, but different from the two big groups of non-carbonaceous and carbonaceous. So this might indicate that the parent bodies of these NEOs formed at a different isotopic reservoir, perhaps at very large distance from the Sun. But as I said, we will talk about the NEO population as a whole. And to introduce that subject, I would like to show this animation of the inner solar system, where you have the Jupiter on outside and the inner 4 terrestrial planets on inside. And of course, there is this major belt between the orbits of Mars and Jupiter, the asteroid belt, or main belt as we call it, where they are about 1 million bodies larger than 1 kilometer in size. If you pay close attention to this region, you can also see a few sprinkle bodies here in the terrestrial planet region, and these are NEOs. I show this to point that the main belt is much more massive than the NEO population. Now, if you zoom in and show the orbits of the known NEOs, it's a mess. There are lots of them. The Earth is here, and the fact that these orbits intersect the orbit of the Earth means that there is a potential for impacts. However, this potential for impacts is not as large as it might seem from this, because of two reasons. First, the Earth size is greatly exaggerated here, about 2,000 times exaggerated. If I would plot it in real size, it would be just a pixel size on this plot. And the second reason, of course, is that this is just a projection of the 3D orbits. So if some object is passing close to the Earth, it's just a projection effect. In all likelihood, it will be very distant in the z direction. So the potential for impacts is not as great as it might seem. And we will discuss that in detail. Now we have direct evidence for impacts on the Earth. And this is the Chelyabinsk meteorite that happened more than 10 years ago now. It is estimated that was a 20-meter impactor. 20 meters doesn't seem much, but you have to understand that these bodies are impacting at very large speeds. In this case, it's estimated that this body entered the upper atmosphere at 20 kilometers per second. So it takes just a few seconds for this body to traverse the whole stratosphere. So it carries enormous energy in that sense. And indeed, many people were injured, mainly from the shock wave that broken the windows of the buildings in Chelyabinsk, and the glass injured people. So this was an example from 10 years ago. Then when we consider the last century, the most famous event was the Tunguska meteor in 1908. In this case, it's assumed that, or estimated, that it was a 50-meter NEO. There was no crater found, and this is the reason why we think that this object had broken 5-10 kilometers above the ground, released the energy, the shock wave, and that shock wave flattened large areas of the Siberian forest. Okay, so some meteorites really hit the ground, and we have great evidence for that from the craters that have been identified on the Earth's surface. And one of the most beautiful craters and well-preserved craters is the meteor crater in Arizona, not far from Flagstaff. In this case, the radioisotopic dating tells us that this meteor crater formed 50,000 years ago, and the best estimates are that the impactor was about 50 meters in size, so in some sense similar to the Tunguska event. The crater is over a kilometer across and about almost 200 meters deep. This is the distribution of craters on the Earth's surface. If you look at that, well, it is a highly non-uniform distribution. We don't know many craters or almost any craters in the seas, which makes sense because of the impact into a deep ocean doesn't produce a crater, and impact in a shallow ocean, you know, the crater, even if it's there, the erosion is really fast, and we are not expected to find it if the impact happened some time ago. Some of the craters, like Rutherford in South Africa, are very, very old. For the Rutherford, it's estimated that it's about 2 billion years old. So not all the craters are young on the Earth's surface. The most famous crater, of course, is the Chicxulub crater at the Yucatan Peninsula. The Chicxulub crater is almost 200 kilometers across. It happened, it's estimated it happened by the impact of 15-kilometer impactor, so much, much, much larger than what we talked so far, 20, 50 meters. And that, of course, led to a major extinction event at the border between Cretaceous and Paleogene. Now, not all the bodies that come close to the Earth actually impact. In most cases, they just fly, harmlessly fly past the Earth. And a good example of this is the Apophis encounter in 2029. Apophis itself is a 340-meter NEO. It will fly about 30,000 kilometers from the Earth's surface. So that's the distance of geosynchronous satellites, so really, really close to the Earth's surface. There is a scientific interest in this encounter. Both European Space Agency and NASA are sending spacecraft to investigate this object. The interest is mainly because of the tidal gravity of the Earth can change the spin state of the body, and that can tell us something about the interior. There might be also landslides happening on the surface, and that can be also important because of when there is a landslide, it uncovers the subsurface layer, and by spectroscopic and other observations, you can understand the composition of that body, not just the space-weathered surface. I say this is an artist's portrayal because of, in addition to Apophis itself, there are these small bodies flying around, but in all reality, there will be no breakup or there are no other bodies, so it's just one single encounter, and this is in just more artist imagination. Now, to illustrate the effect of that encounter, I have taken Apophis, all planets, plug it in the computer, and evolved it 10 years in the future to show you what the effect of the encounter is. So the encounter, I believe, so this is the Earth, and this is Apophis, and this is the encounter. And as you can see, as a result of the encounter, Apophis changes the orbit. That's because of it receives some delta V from the Earth. If you look at more closely, the pre-encounter orbit has semi-major axis something like 0.9, the post-encounter orbit 1.1, so there's a 20% change in the orbit. Well, this is interesting, but it is just one NEO and one encounter. And you may ask the question, what would happen for population-wise and for many encounters for timescales of millions of years, right? So to illustrate that, I have taken all the 1,000 biggest NEOs that we know of. These are the red dots in this plot. This is the semi-major axis indicating how large the orbit of each NEO is. So small orbits on the left side, big orbits are on the right side. These are the planets, Venus, Earth, and Mars. And on the vertical axis, I plot the eccentricity, which tells us about the elongation of the orbit. So circular orbits, like the planetary orbits, are at the bottom of this plot, and the highly elliptic orbits are towards the upper end of this plot. These are some of the lines of the Mars crossing, Earth crossing, and Jupiter crossing. And this solid line is where the perihelion of an orbit is equal to 1.3, which is a formal definition of NEOs. Everything above this line we call NEO. Everything below this line is a main belt asteroid, but it is just a IAU formal definition. So what happens if we run this simulation in the future? So this is the result of the simulation. The time is running in millions of years. You have the number of surviving bodies, and you can see a lot of action, right? The orbits are changing all the time. And that's the effect of partially of the encounters with the terrestrial planets, but there are also some other dynamical effects, like effects of resonances and stuff like that. So what we learn from this is that the NEO population is relatively short-lived. At the beginning, we have 1,000 objects. If you follow the evolution for something like 10 million years, we have half of the objects left. So the half-life, dynamical lifetime of NEOs is about 10 million years. Which is stunning, right? Because of, why is that so? What does it mean? Does it mean that the NEO population, we are living in a special time in the solar system history where we have many NEOs, and 10 million years from now, there will be only half of them, and if, 100 million years from now, there will be a tiny population of NEOs. That would seem strange. Usually as a scientist, you want to assume some steady state, think that the population you see exists is a typical state, right? And if you do so, you have to admit that the NEOs have a source. As they escaped, they must be replenished from a source. And that source, of course, is the main belt. So this plot shows the relationship between NEOs and the main belt. This is the formal line of formal definition of NEOs at 1.3 AU. Everything here is an NEO, everything here is the main belt. Now, if you, it's the same plot, semi-major axis and eccentricity, right? So if you look at the distribution of NEOs, you see that they are not uniformly distributed. There is this excess of NEOs at the perihelion distance about corresponding to the Earth, about 1 AU. This is an observationally biased population. It turns out that bodies with these orbits, they come very close to the Earth, and even if they are small, 50-meter bodies, they are faint. When they come to the Earth, they can be observationally detected. So the detection efficiency is significantly higher in this region, and that's why we have this. And this highlights the importance of considering observational biases in the study of NEOs. Now, the main belt is a much larger population. We have seen it in that initial animation. In fact, the main belt is 1,000 times larger population-wise than the NEOs. Now, if we want to consider the main belt as a source of NEOs, we can do the following calculation. We know that there are about 1 million asteroids in the main belt. And from dynamical simulation, we know that 30%, that the main belt loses 30% over 4.5 billion years. So it loses about 300,000 asteroids larger than 1 kilometer over the age of the solar system, right? That's quite simple. So this is the source. Then the target, the NEOs. We know that there are about 1,000 NEOs larger than 1 kilometer. And we know from the previous simulation that they lose half of the population in 10 million years. So you need to keep this target population in a steady state, you need to inject 500 NEOs larger than 1 kilometer every 10 million years. And there are 450 intervals of 10 million years in 4.5 billion years. So this simple multiplication gives you just over 20,000 bodies in total. And when you compare the source and what you need, you're happy because of these two numbers are about the same order. Okay, so this is just a back on the envelope calculation that the main belt can be important source of near asteroids. But then you ask the next question. How the main belt asteroids evolve to become NEOs? What are the dynamical pathways from this region to NEOs? Well, it turns out that this pathway has two stages. This was not something that was understood only 3 decades ago, but there was enormous progress done in understanding the source of NEOs and meteorites in the past decades. So there are two stages to that. The first stage is the semi-major axis drift of main belt asteroids due to a radiation effect called the Yarkovsky effect. I have spent quite a bit of time last Thursday discussing the Yarkovsky effect in context of spreading the asteroid families and for the source of meteorites on the Earth. So if you are interested in more detail, please go to the recording from the last lecture. I will not spend too much time about it. I will just say that, well, Yarkovsky drift is a radiation force, it's a size-dependent effect. Smaller bodies drift faster, bigger bodies don't drift that much, and this just moves the asteroids in the semi-major axis. So that's the first stage. The second stage is the effect of resonances. It turns out that the main belt is crisscrossed by different resonances. Most of them are resonances with Jupiter. These are orbital resonances with Jupiter. What they are is they are places in the main belt where the orbital period of an asteroid is in some integer ratio to the orbital period of Jupiter. So, for example, this resonance it's located at 2.5 AU, that's called 3:1, is a place where the asteroid orbit has orbital period of 4 years, which is exactly 3 times less than Jupiter's period. That's 12 years. And it turns out if that's the configuration, then that's the place where the gravitational perturbation of Jupiter can accumulate and create big changes in the angular momentum or eccentricity of the asteroid. I will show an example of that in a second. So there are all these resonances which provide pathways from the main belt to NEOs. They are weaker resonances in the inner main belt, and there is also this resonance denoted Ni6. It's like the orbital resonance I just described, but in this case, it doesn't involve the orbital periods, it involves the precession periods, precession of the orbits. But it acts in much the same way like the normal resonances. So to give you one example of a body that is injected into the 3:1 resonance at 2.5, here you have the orbit, this is the Earth, and you can see that, well, there is a lot of hesitation, but the eccentricity is changing all the time, and at some point in the simulation, the body just jumps and evolves into the NEO space. where it has encounters with the planet, starts evolving along this complicated trajectory. And if you wait long enough, this body actually impacted on the Earth. So this is this two-stage process. Yarkovsky drift to reach resonances, and then resonances transport you like highways to the NEO space. Now, the goal here is to build a complete model of the NEO population, meaning the model for the orbital distribution, model for the magnitude and size distribution, albedo distribution, to tell us how frequently the NEOs impact on the Earth, what is the incompleteness of the NEO population, which is an important question as well. So how do we do that, right? Ideally, we would like to follow the physics, the dynamics that's there. We would like to follow Yarkovsky bodies drifting by the Yarkovsky drift and the evolving to the NEO space. But this is pretty complex, right? Because of the Yarkovsky drift is a complex radiation force that depends on the size, it depends on thermal conductivity, it depends on the spin state of each body, and we don't know these quantities really well. So the next best possibility is to just ignore the Yarkovsky effect. The Yarkovsky effect also takes a long time, so we would be wasting CPU time, computer time, just following these objects before they reach resonances. So it will be also very inefficient to build the complete model. So the next best choice is to ignore the Yarkovsky effect, assume that the resonances are actual sources of the NEOs, and build the model just from following bodies from individual resonances. How do we do that? This is an example, again, from the same resonance I mentioned before. 3:1, sitting at 2.5 AU, the same plot, same major axis eccentricity. This is the place where Jupiter perturbations produce instability and increase of the eccentricity. The 3:1 resonance is V-shaped because of the coupling between the asteroid orbit and Jupiter orbit is stronger for larger eccentricities. That's why the resonance open. Now, we know that these main belt asteroids should drift into the 3:1, and this from the left should drift into it. But we don't want to simulate it. But we want to respect what the eccentricity and inclination distributions of these bodies are close to the resonance, because of when they drift, they will have those eccentricity inclinations. So what we do, we take these stripes on the borders of the resonance, build an eccentricity inclination distribution from that, and then inject a very large number of bodies into the resonance. This large number is needed because we want a large statistics from this model. It's a statistical model. If you would just follow 1 or 2 or 3 bodies, you wouldn't build any statistics from that. So you need a very large number of bodies. Then you plug it in an n-body integrator and follow the evolution as these bodies leave to the NEO space. To show that what happens, this is the same plot, but now I've expanded the region so that you can see the NEO region as well. And I will not show you all the 100,000 bodies because that would be too much. I will just show you a selection of 100. So this is what happens. So in addition to the position of all the bodies that are in green, I also show the path they have taken and recorded in these dots as these bodies from the 2:1 populate the NEO region. So it is quite complex, and to populate the NEO space, you really need large statistics. Okay, what's the next step? The next step toward building the NEO orbital distribution from this is binning. You have the incoming NEO, perhaps coming from the 3:1 resonance. It evolves. We have the orbital domain of the NEOs divided into bins. We consider the semi-major axis, eccentricity, inclination, and ignore the orbital longitudes. And in each of these small boxes, when the body passes through that box, we record it as the body spending some time in the box. And we do that for all the bodies, all the resonances, and build up a distribution out of it. This is what you get. The bins are pretty small, so you can't see them quite nicely. Maybe this rugged border of the distribution show the sizes of the boxes. The binning is done in 3D, in semi-major axis eccentric inclination, to have the complete understanding of the orbital distribution. But these are just two projections in the eccentricity and inclination space. The redder areas is where bodies spend more time from the 3-to-1 resonance. And as expected, when they leak into the NEO space, they have roughly the same major axis of 2.5, which is the location of the 3-to-1 resonance. And then they spread by planetary encounters and other dynamical effects. What we do here is that, well, we call this residence times because of, in a sense, this is how much time these bodies spend on different orbits. But in reality, these residence times, PJs, are normalized to 1 NEO coming from each source. So they are what we call the probability density functions, just normalized to 1. They express the probability of the NEO to be on any possible orbit. Okay, so this is the case of the 3-to-1 resonance, but we know that there are many sources of NEOs, all these resonances. So the same thing needs to be repeated for all the different sources, and this is the examples of the orbital distribution from the new 6 source, a little bit on inside of 3-to-1, the 3-to-1, another resonance with Jupiter, which is at 2.7. We go for all the sources we can think of that were pointed in the past publications, A to 3, 2 to 1. We include comets because of some of the NEOs can be cometary in origin. And we also include some special sources like Hungarias and Phoceas. Both these sources sit in high inclinations. So if they produce NEOs, they produce NEOs with relatively high orbital inclinations, reaching up to 40 degrees. And in addition to that, we consider weak resonances with Mars in the inner asteroid belt. The previous work has pointed out that they may be sources of very large NEOs. So the idea here is to be as complete as possible and include lots of sources and then combine them together to produce the orbital model of NEOs. Now, this is the most complicated slide I have, but it is an important slide. Just to that you understand how you build a complete model for NEOs. So this quantity is the complete model. It is complete model in the sense that it accounts for the orbital and magnitude distribution of NEOs, but it also accounts for the observational detection of NEOs by a telescope. So it's not only the model of the population, it's also model for the detection. And once you build that model, you can directly compare it to observations, right? It has several components. It has these residence times maps from different sources. It turns out that you have to include NEO disruption close to the sun, and that's the reason why they depend on size or the absolute magnitude. But in a sense, it's the same thing that I showed before. These are the residence time maps. To combine these maps into a model, you need to multiply them by contributions of each of the sources to the NEO region. Because we don't model the Yarkovsky drift, we don't know what these numbers are. These could be constants, but previous work suggested that the contribution of different resonances is a function of size. Some resonances produce larger NEOs, some smaller NEOs, so therefore these coefficients are also dependent on the size. And this is a sum over all the sources, and we have 9 to 12 sources that we consider. Now, these coefficients are not known a priori, and it's something that has to be fixed by fitting the model to actual observations. So this is a free model parameter. Then this is normalized to 1, so it has to multiply by the absolute magnitude distribution. Again, we don't know what it is. We can parameterize it and then fit to observation to to obtain this distribution. And finally, we have to account for the detection probability. Of course, we have to account for it because of when we want to compare the model with telescopic observations, we have to account for the detection probability. So the idea of all this is to build this model, compare it to observations, and establish what these parameters are, and then based on this model, we can calculate the impact rates. Okay, I highlighted the importance of telescopic observations. Now, what are they? So they are, in the past decades, 3 most important observational surveys of NEOs. Pan-STARRS in Hawaii, Catalina Sky Survey in Arizona, and the Space Wide Field Infrared Survey Explorer, or WISE. This is the number of NEOs discovered by each survey over the past 30 years. Catalina Sky Survey is green. Well, this is the number of NEOs discovered by each survey every year. Catalina is green, Pan-STARRS is in purple, and you can see that over the past 2 decades, these 2 surveys are the most important. They discovered together something like 2,500 NEOs each year. So if you are building a model, ideally, you would like to take these 2 surveys into account. Unfortunately, Pan-STARRS has a really complicated observational biases and strategy. So we are not able to use the Pan-STARRS data in the end, but we use the Catalina data, focused on the Catalina data. These are some of the NEO detections by the Catalina Sky Survey. On the left side, you have the ecliptic longitude and ecliptic latitude of the bodies discovered by the survey, NEOs discovered by the survey. In May 2016, the camera of the Catalina survey received an upgrade. That upgrade increased the sensitivity for faint NEOs. And also, as a result of that upgrade, the field of view of the Catalina Sky Survey increased, and the strategy changed. Initially, they were just sampling things to the ecliptic, which is the most efficient way to discover NEOs, because most of them are close to the ecliptic. But once the field of view increased, the strategy included also sampling the high ecliptic latitudes. And of course, the Catalina survey is on the north hemisphere. That's why this cloud is slightly biased towards the north ecliptic pole. Now, these are the number of detections, unique detections of NEOs by the both surveys. And you see that this period between 2016 and 2022 is the most important one, where there are nearly 12,000 detections of NEOs by CSS2 itself. Now, to be able to use this data, one has to understand in detail the detection bias of the Catalina survey. And that's not something I can discuss in just a few slides. Basically, I have skip over it. But I would like to point out that it is a very complicated issue. The question is not only that the survey wants to discover new objects, but it wants to understand how inefficient it is in discovering the new objects. What's missing, right? And that's an important question because of usually you discover just a small fraction of the whole population, and you want to know how big the population is. And there are all sorts of observational biases. The sky coverage is the first one. If you don't look at the whole sky, you can miss a lot of objects. Photometric bias is the second one. If the object is too faint, you will not see it on your CCD because if you are not sensitive enough. If your object is moving too fast over the CCD, the signal gets diluted over many pixels, and then you also don't see it. So you have to go in detail and understand all these complicated issues to get to this point. And this point is a full characterization of the observational bias of the Catalina survey. It comes, it is conveniently here binned in the same way we bin the orbital distribution. So just by multiplying the bias with the expected number of bodies in each bin, we build the biased model. And the bias itself is a function of the three orbital elements and the brightness or the size of the body. On the left side, you have large NEOs, bright NEOs. The H is the absolute magnitude. On the right side, you have small and faint NEOs. Again, this is the detection probability by the Catalina survey. So if you are in the red region, the detection probability is 1. It's almost guaranteed that you will detect the object if it's there. But if you distance yourself from this region, you see that in this place, that's within the Earth orbit, the survey has difficulties to discover objects. So even if they are there, you are blind to them. You don't see them. And the same happens if an object is a very large distance. There is a strong bias towards low ecliptic inclinations. So most of the NEOs you discover here, and you are kind of blind to NEOs that have very large inclinations. And these biases become more extreme if you go to smaller, fainter bodies. So if you are at 50 meters, you really need something that has an orbit very similar to the Earth, stays close to the Earth all the time, and you have good chance to find it. Okay, so we have the orbital distributions from different sources. We have the bias. Now let's put it together and compare with observations. So this is the intrinsic model trial. That's taking the orbital distribution, assuming some weights. We don't know a priori what these weights will be, so we have to sample a lot of possibilities. But by assuming some weights, we can combine it into the model of the NEO population. We multiply that by the detection efficiency, which is this capital calligraphy P here. We multiply it and then ask the question whether it fits Catalina observations. These are the Catalina observations that I just showed, but now binned in the orbital space. And of course, when we try it once, it doesn't fit. We have to go back and iterate this forward model through millions of iterations to establish these coefficients, establish what the size distribution is, and that's just the forward fitting. And we use a very efficient method to sample different possibilities. So then we arrive what we wanted since the beginning, which is the model. So I will be using these plots quite a bit. These are cumulative distributions, semi-major axis, eccentricity, inclination, and the absolute magnitude. But I will also show the differential distribution, which is just the binned number of bodies for small bins in all of these three parameters. So the observations in this left plot are showed by the dashed line, and in this right plot by the red line to highlight a little bit more. The solid line is the best fit. Well, if you look at the cumulative distribution, there are just some tiny differences which are not too significant, but if you look at the differential distribution, you can start seeing maybe some little differences. This shaded area here is just 1 sigma, 2 sigma, 3 sigma uncertainty of the estimate to give you some sense of the statistical errors, right? So what we see here is that, well, the eccentricity distribution and the inclination distribution is pretty good. There is some small wiggle, small excess for 20-degree inclination. Maybe we missed a little bit some high inclination source or something that may happen. There are these bumps in the semi-major axis distribution that the model explains pretty well. Those are not intrinsic features of the NEO model. Those are produced by something called the conjunction effect, when the NEO has the orbital period that's a multiple of 1 year. The configuration that you can see it repeats over time. So if the configuration is such that the body in opposition is at large distance or elsewhere, you just don't detect it. So these are the bumps, and the model describes it pretty well. The magnitude, the biased magnitude distribution works well. I didn't talk about it much. We used cubic splines to approximate that and then fit the coefficients of the cubic splines to match the observations. That works quite nicely. Now we are getting to the interesting stuff. We build a model and we can ask all sorts of questions, right? So the first one, I highlighted those alphas. Those are the contribution of different sources, the resonances, right? It turns out that these alphas are strongly size dependent. If you are at 15 magnitude, that may be NEO of several kilometers in size, 25 magnitude, maybe 50, 100 meters, depending on albedo. You see that the 3-to-1 and nu6 are always important, but combined, they contribute to something like 30% of NEOs. But at small sizes, these two sources become extremely dominant. They produce more than 80% of small NEOs. And this finding explains some tension that was between the previous model that were developed independently for the small NEOs and large NEOs. These models didn't agree with each other as for the contribution of the inner belt versus the outer belt, and this size dependence removes that tension. Another significant source are these inner weak resonances, which are resonances in the inner belt. They are typically resonances with the Mars. And as you can see, at small sizes, they are unimportant, but if you go to large NEOs, these inner weak resonances are super important. This has been something suggested by Fabio Migliorini in 1997. And it makes sense because of these large bodies, when they drift, they cannot drift too far by the Yarkovsky force. So they are unable to reach one of the main big resonances in the main belt and escape. They just migrate a little bit, reach the tiny resonance nearby, and then they evolve to the NEO space on a longer interval. So this is as for the contribution of sources. Now, there is a problem. So far, I showed you only the result for the bright NEOs. And those results looked really good when compared to observations. But things change when you go to very faint NEOs, magnitudes 25 to 28. There you can see that for inclination and absolute magnitude, there is not a big problem. The observations are within a few sigma to the biased model. But there is a problem with the distribution in the semi-major axis, where observations show this excess between 1 and 1.5 AU. And there is also a problem with eccentricity distribution, where this bodies in excess in semi-major axis also have an excess in eccentricity for small eccentricities below 0.2. So what is going on here, right? This is the best fit. We work on this for a long time. We tested all sorts of possibilities, and this problem remains. So one possibility is that it is an effect, it's produced by an effect we didn't include in the modeling. And then effect could be the tidal disruption of NEOs during close planetary encounters. So here I have replotted the excess shown in the previous plot in terms of the semi-major axis and eccentricity. I combined the two plots together to show where the excess is. And this is the excess. You can see that the biggest excess is between 1 and 1.5, between 0 and 0.3, 0.4, where the excess is about 20% for small NEOs. This region also turns out to be a place where bodies have frequent and low velocity encounters with the Earth. Frequent and low encounter speeds. And this is a regime where you expect most tidal disruption happen because of the body spends a lot of time within the Roche limit of the Earth and potentially can be disrupted. So this is an illustration what we think it might be happening in this region. Maybe a few 100,000 years, there was a large NEO that passed close to the Earth, disrupted, producing zillions of fragments, and these fragments would remain on the orbits. They would spread over time, of course, but would remain on these orbits and produce the excess. So it is not proven that this is the case, but it is a serious candidate to explain this excess. We built a simple model for the tidal disruption just to test whether this could work. This is the NEO model without tidal disruption, and this is the model with tidal disruption. It is not ideal, but if you compare the left and right figures, you can see that there was a significant improvement, especially in the eccentricity distribution. But the thing is not ideal because of the model produces more peaked distribution. So maybe tweaking the tidal disruption model will improve the fit. But the bottom line is that tidal disruption could be important for NEOs. The model that was developed is called NEOMOD, just to distinguish it from other models that have been developed in the past. And this is the orbital distribution that you obtain. I plot the same as before, but just remove the observational bias. So this is the true underlying orbital distribution of NEOs. And as you can see, it's quite complex as different sources contribute. This is dominated by the faint NEOs, but this is the underlying truth below all the modeling and all the telescopic observation. This is how the NEO population should look like. So this is the orbital distribution. This is the absolute magnitude distribution, right? Again, it's a cumulative plot, shows the number of NEOs brighter than certain age. So, for example, if you consider something like 18 magnitude, you go to this line and you see that there are roughly 1,000 objects brighter than 18 magnitude. That's how you read this plot. So the NEOMOD distribution, the best fit NEOMOD distribution is shown by the solid line. The red line is some of the previous work that was showing or suggesting that the NEOs at faint sizes should have much steeper size distribution. But in that case, they didn't have any data to compare in this region. So Alan Harris and Paul Kodas just extrapolated distribution from this region, and we believe that, well, this is a much more accurate representation of the real NEOs. Now, if you have this, you have the orbital distribution, and from the numerical simulation, you know how many bodies impacted on the Earth. You can calculate finally the impact flux on the planets. And this is Mercury, Mars, Venus in green, and Earth is blue. This is what you get. Again, this is compared to the previous work. Here, the agreement is better, and this is because the impact probabilities change. The impact probabilities are relatively low for large objects. They are relatively high for small objects, and this compensates this difference that we have in the orbital distribution. Now, this is nice, but who cares about this, right? This is the impact flux as a function of absolute magnitude. What we would like really is the impact flux as a function of impactor size. That's what we care about, like how big the impactor size, not about the absolute magnitude. So for that, we need to supplement the model with some information about albedos and sizes. And that's not something that Catalina Sky Survey can give us because of it's just an optical survey. We don't know what the albedos are. But fortunately, there was the NEOWISE back in 2010, 2011, was a space telescope observing at infrared wavelength. So it measures, you know, what the flux at infrared wavelength is, you know what the reflected light is, And from that, you can build a thermal model that will tell you what the size and albedo of that object is. Again, that's not something I can describe in just a few slides. So I just show you the results of that. So the NEOWISE mission detected only in the cryogenic part of the mission, detected only just over 400 NEOs, which is not too many compared to Catalina's 15,000, right? So the statistics is not, unfortunately, not that good, but at least something, right? So, and this shows the distribution of the detected objects. The size of the symbol is proportional to the size of the NEO. And how dark or bright the symbol is proportional to albedo. So, and of course, the magnitude is linked to the diameter through the albedo through the simple equation. Now, if you look at this, well, there is a lot of mixing with lots of dark objects and small objects everywhere. But if you look at it long enough, maybe you can convince yourself that in this region, you tend to have brighter objects, right? And smaller ones. While in this region, you have darker bodies. And this makes sense because of in the outer belt, where the resonances produce these bodies, the outer belt is dominated by dark carbonaceous asteroids. So this trend makes sense from what we know about the composition of the main belt. Now you have to kind of redo the model, including this new information. So we had the binning, now you have to expand the binning to include a visible albedo, include biases as well. The most efficient way to do this is to fix the base model to that of CSS, meaning that the orbital and absolute magnitude distribution will be coming from the Catalina, and then use NEOWISE to calibrate the albedo distribution. And this is what we have done. We parameterized the albedo distribution by two Rayleigh distribution, one that stands for dark and one stands for bright. So these are two parameters, the peak of the dark population, and this is the second parameter, the peak of the bright population. And then, of course, the relative importance of these two populations, which is just the ratio, is a third parameter, right? How many dark, how many bright bodies we have in NEOs. And we combine them together using this equation. This was something suggested in a paper from 2016 and works really well. And then we redo all the fitting again, including bias, NEOWISE bias, to learn what the best fit is and what it gives us for the albedo distribution. I'm not described it in detail. I will show you the result. So this is the best fit to the observed albedo distribution. The WISE detections are binned here, are in red. And the best fit is the black line here, giving 1 sigma uncertainty here, and the fit is pretty good. Unfortunately, the statistics from observation is not great enough so that there is this oscillating pattern. Maybe with future observation, this will be improved, and then we can have more confidence in fitting. In cumulative distribution, it looks pretty well. So this is just to convince you that we have a good model for the Catalina and NEOWISE observations together. What we find is that the albedo of NEOs is size dependent, and this is shown here. The best values, the D is of the dark peak is about 3% albedo, of the bright peak is about 17% albedo. Those two values do not change too much if you consider different sizes. But the proportion, which is given by this fraction, changes. For bright NEOs, or big NEOs larger than 1 kilometer, you get about 30% contribution of the carbonaceous, dark NEOs, and 70% of the brighter. But that changes if you go to intermediate. The fraction of dark NEOs decreases to 20% and then goes to 15%. I put a question mark here because for these small sizes, the statistics is poor, and in some sense, this is just an extrapolation to small sizes. This also makes sense, this trend makes sense in how the NEOs are sampling different resonances and different portions of the main belt, but I will not describe it in detail. This is the size distribution and population estimate for the NEO population. So our best model is given by the last version of NEOMOD. This is the red curve here. These are some of the population estimates. Given that the statistics of the NEO population wasn't great, we tested different models, simple models or more complex models, where the albedo as a function of this, different sources can have different albedo distribution. There is certain variability in these estimates, but it is not great. It tells us what the systematic errors might be. And as a synthesis, this work estimates that they are about 830 plus or minus 60 NEOs larger than 1 kilometer. So slightly less than 1,000 that I was mentioning at the beginning of my talk. And they are about 20,000 larger than 140 meters. 140 meters is the size of interest for planetary defense. So this is nice. This is the size distribution. From that, we can understand the completeness. It is super important to know what the completeness is at different sizes, because once you know the object, you can monitor it as it evolves orbitally, and you can anticipate whether there will be impact or there will be no impact in the next century, for example. But if you don't know the object, you're blind to it, and it can come and hit the Earth, within a matter of days, weeks, maybe months. And so it is important to understand how many bodies are hiding from us. And so you can plot the known population. The red is the estimated population. And when you take simply the ratio of known to estimated, you calculate the observational completeness, which is a strong function of the NEO size. So for example, for 140 meters, which is about here, you go up, and you see that the completeness is about 46%. This means that we don't know about half of these potentially hazardous NEOs. An impact of 140 meter NEO would be devastating for the region of impact. It depends where it impacts. If it's the ocean, it might not be such a big deal. But if it impacts in a populated area, that would be a big deal. So the completeness is one thing. Then you can ask, what is the frequency of impacts on the NEOs, And this is, again, our best estimate given by the red curve. Again, there is some variability between different models, but as a synthesis, you can estimate that an impact of a kilometer-sized NEO on the Earth is expected once in 640,000 years, which agrees pretty well with previous works on the subject, including Morbi's paper not long time ago. For the potentially hazardous bodies, 140 meters, you have this 20,000 year interval, which is pretty long, right? So, for example, if you ask a question, how likely it is that we have one impact over the next 2 centuries, it's just 2 centuries divided by 20,000 years, and this gives you 1%. So the hazard is not too big, but you have to fold in also the consequences, which would be important. Now, once you have that, you can ask the question, for example, how often we get 50-meter impacts. We know that the meteor crater was produced 50,000 years ago. From this work, following this 50-meter, we get 200 impacts in a million year, which means the average time between impacts should be about 5,000 years. So since this impact, there should be about 10 impacts on the Earth of this size. Of course, most of them would happen in the oceans. There should be 2, 3 that happened on the land, and it turns out that there are 2 impact structures similar to this one that have been dated and have ages younger than 50,000 years. So that makes sense. Other things that you can do is to compare the estimates with other data sets. here we compare the impact flux on the moon with the crater counts on the lunar surface. What people do is that they, from Apollo 14, we know that this cone crater formed something like 40 million years ago. So the ejecta blanket just covered the surface at that time, and whatever crater is on the surface should be younger than 40 million years. So then you count these craters, how many of them they are, and from that you infer that that many craters form over 40 million years. And this gives you a flux on the moon. And different works disagree on what the counting area should be, count craters differently, and therefore there are some slight differences in these estimates. These dots and the dashed line come from the Hartmann production function. The solid line is the Neukomm production function. There is a slight disagreement. And the NEOMOD kind of runs in between, and that is slightly shallower than the Neukomm. So there is a relatively good agreement between these data sets. So this works quite nicely, but again, there is a problem. The problem is when we compare our inferred impact flux with the actual measurements or the observations of bolide detonations in the upper atmosphere. So this is an image of one meteor seen from the International Space Station, but they are dedicated satellites. They monitor the impacts. Most of these applications are military, but these data have been released. So, and they have been analyzed in this recent paper by Cho and Brown. What you have in the data set is just like how much visible flux hits the detector. From that, you have to infer how much energy was deposited in the visible, and how much kinetic energy it represents, and from that you have to infer size. So it's not that you know the size, you have to infer it from these observations, but people do it as well as they can. And when they do that, and also calibrate it on acoustic measurements and stuff like that, they get this curve. It's the data points, and the red is the best fit. So they get something like this. 10-meter impact should be, there should be happening with the average interval of about 3 years, right? Relatively high flux. But when we plot the NEOMOD results and also the results of other recent models, they kind of agree, inferred from telescopic observations, they kind of agree with each other. But the problem is that they are significantly offset from the bolide observations. So this is a major problem with a comparison between observation of impacts and the telescopically observed impacts. And it's not very clear to me what is causing this. One possibility that we looked into is that the tidal disruption increases the impact flux. This is the model I mentioned in the first half of my talk. An example of what the fragments of tidally disrupted NEOs should look like in the space. There should be this displays. This is not biased, but when you bias this, then you obtain that excess, you resolve that excess. But when you look at the size distribution or the impact distribution, then you see, well, there is a difference. If you don't include the tidal disruption, you have the solid line. With tidal disruption, you have this dashed line. But the difference is not large enough to explain the order of magnitude excess in the bolide observations. So it is still not very clear what's causing this. Just a final note. This excess happens at 10-meter impactors, which doesn't seem particularly impressive, right? Who cares about 10-meter impactors? But then the question is how the bolide measurements continue to large sizes. We don't know because there are not enough impacts here. We would have to monitor the impacts over thousands of years to see how many of them there are. But the NEOMOD is predicting this blow curve, right? So what happens here, how the bolide curve transits to NEOs, it's not very clear. But the bottom line, again, is that this problem can be affecting not only 10-meter impactors, but also the impactors that we care about. And of course, the NEO surveyor will be launched in 2027, should start operation in 2027. The goal of a NEO surveyor is to detect 90% or more of the potentially hazardous NEOs. So this will be a very useful tool to understand if the decameter problem is on the side of observation or maybe on the side of the understanding the bolide detections. So these are some of the key points to remember. NEOMOD is a good model for NEOs. It's built based on dynamical simulations that are calibrated on observation. This is the best approach to the problem, where you take the best from theory and the best from observations, and you combine them to get you a robust model. There is some evidence for tidal fragmentation of NEOs during close encounters with planets. We get estimates that the average time of impacts of kilometer-sized bodies should be something like 640,000 years. For the potentially hazardous 140-meter-sized impactors, the interval between impacts should be about 20,000 years, and only half of these impactors are known at this time. And that's where the NEO surveyor can help enormously. I didn't have time to talk about large impacts, like the ones of Chicxulub scale impacts. Perhaps the size is larger than 10 kilometers, but a work related to the subject suggested that the frequency of these impacts is not as great as you would think based on the dating of Chicxulub. One of these impacts happens every 250, 500 million years. Half of these impacts are carbonations and start their journey beyond 2.5. That's part of that size dependency of the sampling of the main belt. And this makes sense because of the Chicxulub impactor itself was a carbonaceous body, probably coming from the outer part of the main belt. And then I highlighted decameter gap problem, which can be caused by a combination of factors, including tidal disruption, perhaps some problems with the detection efficiencies, or some missing sources. So this is all for today. This was the last talk, and I guess I will wish you happy holidays.